Oh, hello. I wanted to tell you a little bit about a paper that I wrote and published last year. The paper is called "The Modelling of Shockwave Pressures, Energies and Temperatures Within the Human Brain Due to Improvised Explosive Devices," in parentheses, that's IEDs, using the transport and Berg's equations. And I wanted to explain how I arrived at this expression up here. We call this equation star for the pressure. Um, Now, I arrived at this equation for the pressure. Really, it should be called P of Tx, but it doesn't really matter because it's just notation as long as you know that that is pressure. Now that arises out of the Berg's equation, and from the Berg's equation, out of the simplified Navier-Stokes equation, which is this. And normally the Navier-Stokes equation is just the Berg's equation, u sub t plus u times u sub x equal to minus dp by dx. Now, in my research, I did away with that minus sign because the result there is both positive and negative anyway. And so I just stuck with a positive sign in that case. Um, the way things turn out, that would get absorbed anyway into the constant here in this equation. But I'll take you from here to here now because it requires a little bit of understanding of the method of characteristics. Now, for the shock situation, C is equal to 0. Okay? So we've got u sub t plus u sub x is actually equal to 0. But I don't like to put 0 in there because when you use the method of characteristics, you have dt over 1. That's the coefficient there of 1. And that's equal to dx over this coefficient here, which is a u. So let's just highlight that. So the coefficients of u. So the coefficient of 1, coefficient of u, and that is equal to du over a constant. Now, in my research, I explained how you can form three ordinary differential equations from this system here, and if I just rub that out so that I allow a little bit more board space, right, we have dx by dt, so the dx by dt here, which is equal to u, we have du by dt, which is equal to c, and we have du by dx, which is equal to c upon u. Now again, for the shock situation, c is equal to 0, so we've got du by dt, and in this case the du by dt happens to be equal to this because c is equal to 0 there, as well as the fact that it's equal to 0 there. So it's equal to du by dx equal to 0. And when you integrate that, you get basically you get u is equal to a constant. We say it's a constant of some generalised coordinate system in terms of x and t, which we call k. Okay, but we can just write that u is equal to a constant there because it is. Now, it turns out that when we solve the rest of this system, when we come to this Navier-Stokes equation here, we've got I'll just rewrite it here. Let me get a red pen. So we've got u sub t plus u sub, excuse me, u sub x equal to, well, I'll just write dp by dx there. Now, again, solving by the method of characteristics, let me go to a blue pen this time. We have dt over 1 equal to dx over u, and over here we have du over dp by dx, and I'm just writing that straight d's. Right, now we know that u is equal to a constant, a. Now this part here in the denominator is dp by dx, so we really want an ordinary differential equation in x and x only. We don't want to equate this with the time t, because that really overcomplicates it, and at this stage we don't really want to be integrating with respect to t when we've already got a derivative of x involved. So what we do is we take these two equations here so that we have du by dx equal to 1 over u dp by dx. Okay, now I'm just going to erase this little bit of the board up here if I can. I'm afraid it's a new board, and the pen isn't coming off as easily perhaps as it should. But anyway, that should be okay. So, okay. We've now got du by dx is equal to 1 over u dp by dx. Integrating du by dx with respect to x, that's equal to 1 over u, the integral of 1 over u dp by dx dx, right? But this u we know is a constant a. So we can just replace that u with a. It's just a constant, so it simplifies matters. Now, that cancels with that cancels with that, and we're left with the integral of du equal to 1 over a times the integral of dp. Okay, right, green pen. This integrates to simply give u equals 1 over a dp. Right, so we've got an expression for u. Let me try and get rid of, let's just erase this. Right. Right, so we have here, and perhaps I should have stated this at the beginning, but we have a boundary condition. This is our boundary condition. I'll rewrite it here. U of x is equal to alpha 1 e to the minus omega x sine omega x. Now, if you read my paper, you'll see how I solve that, because basically what you do is you substitute in the general coordinate system, k, and sorry, that should be a k. K sine omega k. Now, eventually, what you get when you work out what k is, you get this equation here, right? With these terms in here for k. So it turns out that k is equal to x minus x naught over a omega t minus t naught plus 1. And the same here as well. But how do we know this is equal to pressure? Well, we can see from the boundary condition, which I've rewritten as this expression here. We can see that u of k is equal to, you say u of x, it doesn't really matter. But we've got u of k is equal to 1 over a. And by the way, I should have integrated that to get p. So du is equal to 1 over a times the integral of dp. U is equal to 1 over a times p. Right, okay. Sorry about that, I do make mistakes. So we've got 1 over a p for the velocity, but we know that the velocity is equal to alpha 1 e to the minus omega k sine omega k. So therefore, this term here has to be equal to that, and by implication, the right-hand side of that equation. So what we have is 1 over a times p equal to alpha 1 e to the minus omega k sine omega k. And if you just multiply both sides of that equation by a, you get p equal to alpha 1 a e to the minus omega k sine omega k. And of course we can just do you remember when I said that if we have a minus sign in that term there, well, we would end up with the minus sign in the constant term there. So we normally would have u equals to minus 1 over ap. But the thing is, you can absorb that minus sign into the constant term, and we can just rewrite the whole thing as p equals alpha e to the minus omega k sine omega k, right? And that basically is how we get from that to that to that, bearing in mind that k is equal to x minus x sub 0 all divided by a omega times t minus t naught plus 1. And the same in this part of the sinusoidal argument as well. And that's basically how we derive the pressure from the Berg's equation expressed in this equation star here, which is in equation 63 of my paper. Again, I'll just highlight the title of my paper again. It's The Modelling of Shockwave Pressures, Energies and Temperatures Within the Human Brain Due to Improvised Explosive Devices, or IEDs in parenthesis, using the transport and Berg's equations. And as perhaps I should have said at the very beginning, this equation star is pertaining to equation 63 on page 3 of that paper that I've just, the title of which I've just read out. It's also the same basically as equation 64. But equation 64 is just an equation without this omega term here. So I hope that has explained a few things for you. And until next time, thank you very much and see you later.